Hello everyone, welcome back. So this time we'll be talking about equations of equilibrium. Like I said last time, you're like, well, we've done this already. Why do we do this again? We're not doing it again. We did the vector form last time. That's why these are italicized, bold, and red. But in reality, those vector equations can be broken down into 6 scalar equations, just like we did with particles in 2 dimensions, where we had our vector form of the forces. We broke it into our x and y equations. Well, same thing here. And luckily for us, that in statics, everything is equal to 0. It's always equal to 0. Some of the moments equal to 0 in the x, y, and z directions. Some of the forces equal to 0 in the x, y, and z directions. So, lucky for us, that makes things wonderful. Now, because there are 6 scalar equations, means we can have up to 6 unknowns. And this helps us. Now, as a note, it's going in that right here. You have all 6 of these equations. It means you get 6 equations, but honestly, when it comes to sum of the moments, you can choose multiple points to take the sum of the moments around. However, that doesn't give you any extra equations. You only get 6 equations that can possibly be different. Everything else will break down until it looks like the same equation. You'll just divide by 2, and it's the same equation now. At first, you might not think that's the case, and maybe sometimes it won't be because you made a mistake. So if you've seen I got 7 equations, you probably made a mistake. Or math just broke. I'm guessing it's the former. So remember that. Also remember that usually sum of the moments is the easiest one to go with. Just pick a point that has a bunch of forces or the line of action of forces going through it. Take the moment around that point. And that will get rid of a bunch of unknowns. Make it very simple to solve. So even though you have 6 equations, don't worry, you're going to have to do oh no, 6 simultaneous equations. That's going to take forever. I don't do that to you. However, you can do that to yourself if you're not careful. So be careful. Make sure that you are trying to simplify as much as you can by getting rid of as many forces as you can. And also look at the order. If there's only 2 forces in the x direction, one that you know and one that you don't know, solve that equation. Make it easy on yourself. So it's not as bad as it may seem. You can do this. I believe in you. Okay, now let's talk about a very strange situation here. Constraints and statical determinacy. Now, this is a fun word. It means, can you actually solve the problem? Can you? Let's look at this one right here. So we have this point B, which is just floating off in space. And we have this point A, which we have a reaction force here. And point B is, not floating off space, it is actually affixed to this ceiling. Now, in this case, we have more supports than are necessary to hold in equilibrium. Technically, we don't need this guy to be holding it in every single direction and getting rid of all the moments. And because this, it becomes statically indeterminate. Statically indeterminate. So what does that mean? It means that I have 8 unknowns, 6 here, 2 here. I only have 6 equations. So I wouldn't be able to solve this with just my equilibrium equations. I would have to have another equation just to save myself, which might be something from solid mechanics. It might be using thermal expansion to figure out how things are solved. It might be, I don't know, there's a whole lot of different equations we're bringing in here. Friction is sometimes another equation you can bring in. So whatever it is, you have to use it. Sometimes you might have more unknowns, you have multiple free body diagrams. That doesn't count. It's per free body diagram. 6 equations per free body diagram. Now, are these statically indeterminate structures used in practice? Yes, they are. You want to have redundant supports. When you have redundant supports, you're going to have a statically indeterminate system. That's where you bring in all of your solid mechanics equations for thermal expansion to help solve them. If you have no idea what I'm talking about there, that's okay. You're not in solid mechanics yet. That's next semester, at least for most of you mechanical. But they are used. It's a real thing. Okay, improper constraints. And this is not because they're making bad jokes. An improper constraint has enough to support all the forces, perhaps, but not all the moments. So in this case, we have 6 unknowns. You're like, well, that's statically determinate. We can solve it. but there's nothing restricting our axis around, or rotation around this axis AB. It can rotate as much as it wants. So in this particular case where P is pointing straight down and this little arc right here is bent straight down, it's stable, but it's not dynamically stable. If I were to switch the force coming out of the page slightly, or into the page slightly, this would begin to rotate with nothing to stop it, and you would not be able to solve the problem. It would not be static anymore, it would be dynamic. So a very similar thing might be that, well, in some cases, it's all completely fine. It might be good as long as, we have a force that is directly perpendicular to this surface at B. That would be fine, nothing would happen. Or if all the forces that are applied to this cancel out, as long as there's only a horizontal force, that can be resisted. But in this case, if we solve it, we have, well, let's see, 1, 2, 3 unknowns. That's way less than 6. This is a 2D problem, so that's all we can get, though. If you look at this, the moment around A is not going to be equal to 0. And because of that, this will not be statically constrained. So if you look at these problems right here, some cases will make it so that this is completely fine. You can do this. This is okay. But other cases it will not. You have to look at what you're creating and say, is this going to be static in all situations? Like, for example, this is a bit different, but if you take a ball and you put it on top of a bowl, if you just perfectly balance it, it is static, it is stable. However, if I barely touch it, it rolls off and falls away. If I take a ball onto the bottom of a bowl, it stays static. And if I roll out of direction, it comes back to the middle. Now this is bringing in dynamics there, but one is dynamically stable, as in the ball is going to return to its equilibrium if I push it a little bit. The other one is dynamically unstable, but statically stable. So you got to think about both. If you have different situations, forces coming from different directions, is it still going to be stable? If you push it a little bit, is it still going to come back to stability? There's a whole lot that goes on here that you have to think about when you're designing something. Now, for you, most problems are going to bring in this whole improper constraints thing, but if you're designing something, it is still important to think about. So, I hope this helps you, and I'll see all of you next time. Bye-bye.